Okay, thanks, and good morning, everyone. Is this blackboard located at a convenient place, especially for people in the back? Can you? Okay, great. Let me start off by just quickly summarizing some of the aspects of last lecture that will appear again today. So we were studying the Kitaev chain, and I spent most of my time focusing on a fine-tuned parameter limit where we set the hopping and pairing amplitudes equal to each other, because in that special limit, the physics kind of just falls out into your lap. Here's the Kitaev chain Hamiltonian expressed in that limit. So there's a chemical potential term for your spinless fermions. And then this somewhat unpleasant-looking thing represents the factorized pairing and hopping processes. Okay, so in this form, it turned out to be extremely useful to decompose your spinless fermion operators in terms of a pair of Majorana operators that are labeled by gamma B and gamma A. And upon using this decomposition, one gets a Hamiltonian that takes the form of a Majorana chain, has a very nice graphical representation as illustrated here. So each of these boxes is a site. So this is, let's say, the fermion operator at site 1, site 2, site n. So the chemical potential hybridized A and B operators within a given site, but the hopping and pairing processes, they hybridize Majorana fermions in a shifted fashion. So the gamma B operator from, let's say, one site couples to the gamma A operator from the next site over. And so from this perspective, you can think about our spinless one-dimensional superconductor as realizing a Majorana chain that has competing dimerizations that are favored by either mu or t. So here's the phase diagram that we deduced. Actually, we deduced this based on thinking about just a periodic chain. So this is a phase diagram as a function of mu over t. So for mu over t less than -1 or greater than +1, we identified a trivially gapped phase that's smoothly connected to just a product state, either the vacuum over here or just a state with one fermion at every site on the positive mu over t end. But in between, we had a much more exciting phase that we uncovered, also a gapped phase, a topological superconductor that, while gapped in the bulk, hosted a pair of zero energy Majorana modes, gamma 1 on one end and gamma 2 on the other end. And we identified that the physics associated with those Majorana zero modes is that they encode a very unusual kind of degeneracy for superconducting systems, consisting of states that have opposite fermion parity. So you have one ground state that has even number of electrons in the system, and another ground state that has an odd number of electrons. And I also emphasized a key feature that really makes this problem relevant for quantum information, and that's that it's basically impossible on very general grounds to identify which of those two ground states your system is realizing via local measurements. And that in turn provides, if you imagine trying to store quantum information in that degenerate subspace, that's a very appealing thing to try to do. All right. So at the special values where mu over t equals -1 or +1, we observed from the periodic chain that the system actually becomes gapless, and those gapless points represent a topological quantum phase transition separating the trivial and topological superconducting phases of this model. So what I'd like to do to start today is to hone in on those topological phase transitions and try to understand the low energy physics that emerges at those quantum critical points. And just to be concrete, I'm going to focus on the topological phase transition that appears at mu over t equals -1. But basically, the same logic that we'll use can be applied also to understand the phase transition at mu over t equals +1. All right, so if I fix mu over t equals -1, then the amplitudes, at least the absolute value of the couplings here and here, become the same, which you can kind of understand from this pictorial representation here, means that those competing dimerization tendencies favored by mu and t, they just compete to a draw. And basically, that's why the system becomes gapless. So let's park ourselves at mu equals -t. The critical Hamiltonian that arises in that case, I'll have an overall energy scale T that I'll just pull out from both terms. So I'll get a minus I T over 2, sum on x. And then the rest can be written as gamma bx times gamma a x plus 1 minus gamma ax. All right, so this gamma ax plus 1 piece, that just represents this piece here. And then the gamma b times minus gamma ax, that's just this thing with the minus sign arises because we've taken mu equals minus t. Okay. All right, so now, if you want to focus on low energy physics, that means you should look at the system not on ultra short scales, but rather in some coarse-grained limit. So now I want to take that lattice model and just, in the simplest way possible, just kind of zoom out, coarse grain over lattice sites, and promote these lattice operators to continuum fields. Right? And in this case, you can do this in a very straightforward fashion. So in the continuum limit, basically this gamma bx operator will just become some continuum field that are labeled by gamma b without a subscript x. The sum on x now should become an integral. And then this difference of gamma a on two adjacent sites, that becomes a derivative with respect to x of now a continuum field gamma a. Okay, so this is the form of the low energy Hamiltonian that you get upon just applying the most naive coarse graining procedure to that Hamiltonian. So this is technically the correct low energy description, but it's not expressed in a very transparent way. So now I want to just do a simple cosmetic change. Let's trade in our continuum gamma b and gamma a fields for a set of right and left moving fermion fields by writing gamma a or b as gamma r plus or minus gamma l. Okay, so the fact that, so it'll turn out that gamma r is a operator associated with a right-moving excitation, gamma left associated with left-moving excitation. That should not be obvious so far, but we'll see that this is indeed the case. All right, so this is just algebra at this point. I'm just going to plug this expression into the coarse-grained Hamiltonian, and we'll just see what happens. Okay, so we again have a minus it over 2 prefactor out front, integral on x. So the gamma b I replace with gamma right minus gamma left. I have a derivative, and then the gamma a I replace with gamma right plus gamma left. All right, so let's just expand out this product. Okay, so multiplying these two will give me a gamma right dx gamma right. Multiplying these two will give me a minus gamma left dx gamma left. And then I get cross terms. There's this cross term. This looks like gamma right dx gamma left. And then this cross term, which looks like minus gamma left dx gamma right. Okay, so these terms actually cancel, and we can see that in the following way. So first, I can try to recast this piece in the form shown here by in a two-step procedure. So I can integrate by parts to pull the gamma, the derivative from acting on gamma right to acting on gamma left. I'll get one minus sign from doing that. And then I can take the dx gamma left, anti-commute it past gamma right. I'll get a compensating minus sign. And then this will take exactly the same form, but with a relative minus sign. Okay, so these pieces actually cancel. And this is just what we're left with. And I will just write this in a, basically repackaging the prefactor slightly. I'll write this as integral on x minus I h bar v gamma right dx gamma right plus I h bar v gamma left dx gamma left. Okay, so this is a much more illuminating form of equivalent but illuminating form of that continuum Hamiltonian. And here I've just basically defined a velocity. Well, h bar v was essentially taken to be t over 2. Right? OK, so let's try to unpack this a bit further. I think it pays to assume that you have periodic boundary conditions, and then Fourier transform to momentum space, so we can understand exactly what the structure of this Hamiltonian is. And by the way, this may look familiar. So this is actually the right-moving kinetic energy for Majorana fermion, and this is the left-moving kinetic energy for Majorana fermion. You may have seen similar-looking things in the context of the quantum Hall state, quantum Hall edge states, where this you wouldn't have Majorana operators, but instead something like a conventional fermion operator, and we'll try to understand what the difference is from those conventional right and left moving fermions versus these Majorana fermions. And that's what we can do by passing to momentum space. Okay, so we're going to Fourier transform in the usual way. So gamma right, left as functions of x, we'll write as an integral on k e to the I k x times gamma right left of k. So these are k-space operators. Now we know that these real space operators are Majorana fermions by definition, right? So they were just arose from the continuum limit of these lattice operators that were their own Hermitian conjugates, squared 1, and so on. And so we can ask, what do the Majorana properties, hermiticity and the fact that they squared a 1, what do those properties imply for these momentum space operators? Okay, so in particular, the fact that the real space operators are Hermitian implies something very important for our k-space operators. Actually, anyone know what this implies for gamma right left of k?
Gamma k equals gamma dagger minus.
Yes, that's right. So if you look at gamma right left of k, that's equal to gamma right left dagger of minus k. All right, and so you can just take the Hermitian conjugate of this, set it equal to itself, and this will just... Actually, is this clear? I could maybe say another word about that. Does anyone want me to say another word about how this arises? OK, guess not. All right, so this is, I guess this is kind of analogous to if you take a real function and then Fourier transform that real function. The Fourier components have to satisfy a very similar kind of constraint, and so this is just promoted from real functions to Hermitian operators. All right, and physically, it's telling us that the fermion creation operators at momentum minus k are not physically distinct operators from the annihilation operators at wave vector k. And so if you were thinking about Fourier transform of ordinary canonical fermion operators, that certainly would not be the case. Right? So if you take, let's say, C dagger of k, where C dagger is a conventional fermion operator, that would add an electron with momentum k, and C, the annihilation operator, would take away an electron or add a hole. Right? So you would have no such relation. OK, so let's see what this ultimately implies for the low energy degrees of freedom that emerge at criticality. OK, so first we can write the critical Hamiltonian in k-space by essentially observing that minus I dx, that's just a wave vector. OK, so we can almost immediately write down the answer. You can do this more explicitly if you like, but when you Fourier transform, you'll get the form integral on k h bar vk times psi right dagger of k psi right of k minus psi left dagger of k psi left of k. Okay, so if we plot the energy as a function of momentum that comes from this Hamiltonian, we can just read it off. So It was a typo. Yeah, thank you. Yeah, these should be gammas. Okay, sorry about that. Okay, so the kinetic energy we just read off. For the right moving branch, it's just h bar vk. Okay, so that's the right moving branch, and I'm going to draw the negative energy states with a dashed line for reasons I'll comment on shortly. So that's the right moving sector. And then for the left moving sector, we just get an extra negative sign. All right, so that's the spectrum. Okay, so the reason that I drew the positive energy states with solid lines, negative energy states with dashed lines, is that this relation here that links minus k and plus k states tells us that the negative energy states and the positive energy states are not actually physically distinct states. Okay, and in fact, if you want to convince yourself of this fact, you can use that property, use this property here, to rewrite this Hamiltonian, which is currently written as integrating over all k, negative k's and positive k's. You can completely eliminate all the negative k, the appearance of negative momenta from this Hamiltonian, expressing this only in terms of states that have positive energy. Okay. Does that make sense? Okay, so it's useful to, so once again, these states are not distinct from the positive energy states. All right, so in some sense, this is like what we get at this phase transition is half of a single channel wire. So if you just had, let's say, an ordinary single channel wire, you can have a right moving fermion, you can have a left moving fermion, similar to what we have here. But in that case, the positive and negative energy states would be physically distinct. One would be like a hole branch, one would be an electron branch. But because these are Majorana fermions, that distinction ceases to exist. And all we have that are physically meaningful are the positive energy states. Yeah.
So in one dimension, why is the right mover with negative momentum versus the left mover?
Well, okay, so the group velocity is derivative of energy with respect to k, so it's the slope that matters for the directionality, right? And maybe I should have said that, that's the fact that the slope is positive, that's why I call these modes right movers. The fact that the slope is negative, that's why I call them left movers. Yeah, thanks for the question. All right. Anything else about this phase transition? Okay, so you might ask, why did I bother going through this? There's actually two reasons. One, I think it's a neat physics problem, but more importantly for experiment, this by probing, if you're, let's say, interested in hunting for the topological phase, which that's by far the most interesting direction in this area. If you have the ability to, let's say, pass from the trivial to the topological phase, you cross a phase transition, and if you can probe the physics of that phase transition and show that when the gap closes and reopens, and you see Majorana zero modes appearing in the topological phase, that provides much more confidence that what you have in the topological phase is actually what you think you have. And I think Charlie's talk yesterday alluded to some aspects of probing this phase transition in transport. Okay. Yep.
So of course, these are propagating Majorana fermions, but then only at E equals 0 do you have the condition that the particle is equal to its antiparticle.
Yes.
So people always ask me this. I'm asking you, how do you still call them Majораnas?
Yeah. Okay. So this is a very nice question that will become relevant also later. So indeed, if you look at the k-space operators, they generally do not satisfy the property that gamma is equal to gamma dagger, except for one special case when k equals 0. So when you set k equals 0 here, that k equals 0 level is, has 0 energy, right? Because at k equals 0, you have 0 energy. And it has the property of being a Majorana zero mode, which you can think about as just being a Majorana zero mode that's kind of been delocalized across your system. That means that the k equals 0 level actually does not have a well-defined occupation number. Because if you look at gamma dagger k gamma k, that becomes just 1 at k equals 0. But for all finite k levels, they become, they're Majorana fermions in the sense that they're the Fourier transform of a real fermion field. But the finite k levels have a qualitatively different structure. They are particles in the sense that they can have a well-defined occupation number. They can carry well-defined energy. So there's a very important distinction between all the finite k levels and the zero k level. Okay. All right, so the other reason why I wanted to show this is that by understanding the physics that emerges at this quantum critical point, we can leverage our understanding of the Kitaev chain to very efficiently access two-dimensional topological superconducting phases. And that's what I want to do next. What I'm going to show you now actually is very similar to something that Charlie Kane showed, I think in his first lecture, if I remember correctly, when he accessed a Chern insulating phase by coupling a bunch of one-dimensional wires in a fashion that that led to a chiral fermion being left over at the extreme ends. So we're going to see an analog of that in the topological superconducting realm. Okay, so now let's imagine that we have not just a single critical Kitaev chain like we had so far, but now let's consider an array of such wires. Okay, so I'm going to index those wires with a y-coordinate, which will go from 1 to ny. Okay, so each of these lines represents a Kitaev chain tuned to its topological phase transition. And correspondingly, I know that there's lots and lots of low energy degrees of freedom in the system because each of these wires will have a right-moving and a left-moving gapless Majorana fermion. So let's add those in the form of these arrows. Okay, so this right-moving arrow represents the right-moving fermion, left-moving fermion associated with each of these chains. Okay, so now let's suppose that I start to couple these critical Kitaev chains in a very special way, such that I, let's say, take the left-moving Majorana fermion from chain 1 and hybridize that with the right-moving Majorana fermion from chain 2. Similarly, the left-moving Majorana fermion from chain 2, I'll couple that to the right-moving Majorana fermion from chain 3, and so on. Okay, so one can show explicitly, and I have some notes that I'll post online on our Slack channel that actually go through the analysis of this coupled chain Hamiltonian. But maybe it's believable at least that those couplings will allow you to backscatter right-moving modes into left-moving modes, and then just completely gap out the interior of this set of critical Kitaev chains. Okay, so the bulk of this 2D system will become gapped, but something interesting gets left over at the extreme edges. So from chain 1, you have a right-moving chiral Majorana fermion that didn't couple to anything, and up top you have a left-moving Majorana fermion that also didn't couple to anything. Okay, so let me comment on that in 1 second. Okay, so I've cherry-picked, I've fine-tuned, and in such a way that I had enough gapless degrees of freedom such that arbitrarily weak couplings of this type immediately take me to this what is now going to be a two-dimensional topological superconducting phase with a chiral Majorana edge state. If I moved away from criticality, then I would have to have a finite minimum strength for that interaction in order to take me from from a set of gapped Kitaev chains to the topological phase of to the 2D topological superconducting phase of interest. But ultimately, so this, and you can kind of convince yourself that this construction does not require this fine tuning. It's convenient, but it does not require it, because ultimately I get to a gapped phase, and that phase, by virtue of its bulk gap, has some tolerance to departing from the fine-tuned condition that I used to access it in the first place. Yep.
So is there a reason you can't couple the right-moving one-on-one to the right-moving one-on-the other?
You certainly could. So the right-moving to right-moving couplings they're probably benign because they're not really backscattering terms. You could also ask, well, why couldn't I couple, let's say, the right mover here to the left mover from the next chain over? I certainly could also do that. This is my choice to. It's kind of like looking. Actually, maybe I should draw an analogy to what we did in the Kitaev chain. So in the this picture should very much remind you of this dimerized Majorana chain picture that I had. To access the topological phase in the most convenient way possible, I took mu equals 0 and t non-zero, in which case I had these Majorana zero modes that are localized exactly to one side and they're left behind. They don't couple to anything. So this is sort of a higher dimensional version, rotated 90 degrees, I guess, in the sense that now there's something conveniently left behind here and here. And anything else we add, we can add all sorts of other couplings. They will just obscure the physics, but not change the qualitative conclusions. Yeah.
What differentiates this from a weak stackable phase?
This is, so this is an inherently 2D topological phase because I have a single chiral edge state that's going to, this right mover is going to continue to the left mover, and there's no way of decomposing that in terms of a set of lower dimensional topological phases. You could, of course, access a weak two-dimensional topological phase if you just parked each of these Kitaev chains in its topological phase. Then you'd have a bunch of Majorana zero modes, and you would have to add some extra symmetry to protect those Majorana zero modes, but that's how you could access a weak topological phase. But this is a strong two-dimensional topological phase. It's not possible to distill this into some decoupled set of lower dimensional topological phases. Yeah.
So why do you say the bulk is gapped? I mean, shouldn't we expect a delocalized bulk or something because you're at the critical point?
So I started at a critical point, but then I added a perturbation that takes me away from the critical point at arbitrarily weak couplings.
But you said that that's arbitrarily weak. So I mean, it's still very close to the critical point. So I would expect a delocalized bulk state or something.
Okay, so sorry. What I meant there is that you don't have to add a large coupling of this type in order to access the phase. You could add a large coupling if you like, but the threshold for basically accessing this topological phase is arbitrarily weak couplings suffice.
Okay, thank you.
I think there was another question somewhere. Yeah.
Yeah, I was wondering about the symmetry requirements. I was wondering about the symmetry requirements when we couple these change, because I think I remember from a lecture that when we having like only fermion parity symmetry in one chain is already enough to kind of prevent this change from coupling, right?
Well, symmetry is something that you have to impose on your problem. I don't actually need any symmetries here. It could be that, it definitely is the case that if you had time reversal symmetry, you would not be able to do this, right? So I'm certainly breaking time reversal symmetry when I say that I'm going to couple the left mover from one chain to the right mover from the other, but not do the inverse, not couple the right mover to the left mover. Basically, I'm giving up on all symmetries. I'm not, which in turn allows me to add whatever I want, and that's what I want to add. So this is just my choice, and it's just a convenient way to access. To bootstrap what we know about 1D to access a 2D topological phase.
So how would you, or could you, like, put this somewhere in the periodic table, or like, where would this fit?
So this is a. Thanks for asking that question. I think it's useful to ask how in the world, what does that squiggly line mean? So in pictures, maybe it's clear, but if you want to, let's say, write down an electron model, what does that correspond to in, let's say, the original CX fermion language that we build the Kitaev chain Hamiltonians from originally. And I've unfortunately erased some of the key equations, but we know how to go from, let's say, our microscopic fermion operators to these gamma B and gamma A operators, right? And then we know how to go from these gamma B and gamma A operators. Then we know how to go from these lattice operators to these continuum fields, and then we know how to go from those A and B continuum fields to right and left moving fields. So if you trace through everything, you can ask, you can construct a concrete microscopic perturbation that corresponds to exactly these squiggly lines. And that will turn out to have two components in terms of your lattice model. It'll have a component that involves electron tunneling between adjacent chains, but it will also have a component, a Cooper pairing component that takes a Cooper pair by taking one electron from here, one electron from here. And importantly, so that'll also be p-wave-like, which is forced on us by the spinlessness of our fermions, but there will be a relative phase factor of I in front of that pairing term compared to the pairing term that you have within each of these chains. Okay, so if you want to place this into more familiar language that you might see in these periodic tables, this corresponds to the topological, weak pairing topological superconducting phase from a spinless P plus IP superconductor, okay, which doesn't require any symmetries.
Thanks.
Sorry, did you say that the Cooper pairs are between the pairs are made out of fermions from different chains?
Both within chains and between chains. Yeah, and so if let's say the pairing potential is px-like within each chain, it's going to be ipy-like between chains. I actually have some aside in my lecture. I wasn't going to go through this, but in my lecture notes, I have there's half a page of, or maybe less than that, to show that what I just said is true.
So at the end, it's by construction, right? It's not the natural way of you would expect these chains to couple and put them next to each other, right?
You probably would have to work hard to do this. Yeah. Yeah, so this, I have the luxury of being a theorist. I wouldn't tell Charlie, okay, this is how you do it, go make it. It's more complicated than that. All right, so let's just zoom out a bit. And instead of viewing this system as composed from a bunch of critical Kitaev chains, let's accept the fact that we've gapped out the bulk and we've been left with a right-moving chiral Majorana fermion at the bottom edge, left-moving at the top. And let's just go to a finite planar geometry. Okay, so here's my two-dimensional topological superconductor. Bulk is gapped. I have a right-moving mode down below, a left-moving mode up top, and by probability conservation, essentially they're guaranteed to continue along left and right boundaries. So we can, based on what we did here for our critical Kitaev chains, we can immediately write down the corresponding edge theory, gapless edge theory. I'll write this as an integral on a coordinate u, so u specifies where you are along the boundary of the system. Put a factor minus I h bar v. Gamma is going to be the Majorana fermion field that describes that gapless edge state. And I'll have a gamma du gamma term. Okay, so this is, you can just think about this as you've taken, let's say, 1/2 of the edge theory of the non-critical theory that we had in a single Kitaev chain. Okay, so we can immediately read off the energies associated with this gapless edge theory. Once again, just identifying minus I times its derivative as a momentum. The energies are just E equals h bar vk. And so if we plot that energy versus momentum, it looks something like this. And once again, I'm using the fact in this picture that this is a Majorana fermion field as opposed to a canonical fermion field. And so the positive energy and negative energy states are no longer distinct. Okay? And so again, it's useful to think about this as just, you eliminate the left mover, say, and you're just left with a right mover in a critical Kitaev chain. All right, so this, I mentioned the connection to half of a single channel wire. So this maybe looks reminiscent of an integer quantum Hall edge state, which would just have a single let's say, chiral fermion. Since the positive and negative energy states are not distinct from one another, you can think about this chiral edge state as being half of an integer quantum Hall edge state. Yep.
Do you break down the system into you have a px and an ipx?
Yeah. The py.
Or py?
Yeah.
Oh, you have the px and ipy.
Yeah.
And then you said pk.
Yes, exactly. How was time, by the way? Fantastic. Okay. All right. So now I want to ask what I find to be a very interesting question. So when I drew the spectrum, I was implicitly assuming that our system size is big enough so that I can ignore the discreteness in that spectrum, right? But we know that if you had a finite size system, there's going to be finite size quantization. There's only going to be a discrete set of k values allowed, and correspondingly, instead of getting a continuous line of allowed energies, you'll just get a discrete set of energies. And so what I now want to ask is what happens when you include a finite perimeter. Exactly how does this edge spectrum get quantized? So I'm going to turn this into a multiple choice question because there's exactly two options for what it can possibly look like. Okay, so let's call the perimeter L edge. Okay, so option A is that these Majorana fermion fields here, they could exhibit periodic boundary conditions. If they exhibit periodic boundary conditions, that means that if you look at the Majorana fermion field gamma evaluated at U plus L edge, that should be the same as gamma of U. If you have periodic boundary conditions on these fermion fields, then the continuous momentum variable here should become quantized. It should be restricted to discrete values kn, which take the form 2 pi over L edge times some integer n. Okay, so if that's the case, then we should only think about certain discrete values of k. So for n equals 0, there would be a 0 energy level. For n equals 1, we'd have some finite energy level, n equals 2, and so on. And then we'd have the negative energy, not distinct pieces as well. All right, so the only other option is that maybe, for whatever reason, maybe these Majorana fermion fields have anti-periodic boundary conditions instead of periodic boundary conditions. anti-periodic boundary conditions would imply that gamma of u plus L edge is not equal to gamma of u, but rather gamma of minus gamma of u. All right, so if that's your if that's your boundary condition on your chiral fermion, then the k's are discretized in a slightly different fashion. They'll be constrained to the form 2 pi over L edge times integer plus a half. Okay, and this plus a half will ensure that when you that this minus sign gets accrued when you go around the boundary.
Sorry, I'm not sure what this means, because I would have just thought it. Does it matter that? Doesn't it just go round and round? I'm just very confused.
It does.
By applying boundary conditions to.
Yeah. Well, if you don't fix boundary conditions on your Majorana fermion fields, then you can't figure out what the discretized level spectrum will be.
But even though it doesn't scatter, you still apply boundary conditions?
Yeah, certainly. So
I see. Okay, I did not know that.
Yeah. No, actually, this is very important for reasons that you'll see shortly. Yeah, this may sound like a very cryptic, useless exercise, but we'll see that there's a very big payoff that will come shortly. All right, so if you happen to have anti-periodic boundary conditions for whatever reason, then the set of allowed energies is shifted compared to what we have here. So for n equals 0, you actually have a finite k. For n equals 1, you'll have another k, and so on. And you kind of miss the k equals 0. So this set of energies, or this set of k states, is just shifted relative to what you get for periodic boundary conditions. And the reason I say that these are the only two options is that that descends from the fact that these are Majorana fermion operators. Gamma, these real space gamma operators are their own Hermitian conjugate, so you're not allowed to add, let's say, a complex phase here. Okay, that would be the most general boundary condition you might try to append, but in order to maintain the reality, the hermiticity condition of those fermions, all that you're allowed to add here is a plus sign or a minus sign. Okay.
Haven't you said that the occupation for zero momentum Majorana doesn't make sense? It's like, isn't
okay, so hold that thought, please. So I wanted to give this as a, this is a multiple choice question, and so just think about it for a second. I want to. Okay, so we have to. So the hard way, if you wanted to work hard and you were skeptical and weren't sure how to proceed, you could always, let's say, put this model on a computer, diagonalize it, read off the spectrum, and just see, whether this edge spectrum looked like this or like this in a finite system. But we don't have to work hard, based on things that we've gone through in today's lecture and yesterday. There's only one tenable choice, actually. Okay, so it was already kind of hinted at based on the question that I interrupted. But I'm going to take a vote in a second. So who thinks option A?
What's the question again?
A or B? Yeah. So this is, okay, so here's my problem. I just have a two-dimensional topological superconductor on a plane. There's an edge state. It has some discretized level spectrum that either will look like this or it will look like this. It depends on what boundary condition the Majorana fermion exhibits. And one of these is catastrophically bad, and the other one is okay. So we need to figure out which is the right option.
What is the definition of catastrophically bad?
That's for you to decide.
Because it's kind of like, if we know what is catastrophically bad,
Yeah. All right, so option A, who likes option A? Who likes option B? Okay, amazingly large fraction of voters. That's wonderful. All right, so I agree with everybody who said anti-periodic boundary conditions. And I don't know, do you want to say what you were... I think you had identified the catastrophe that arises with periodic boundary conditions. Right? It's that you have a Majorana zero mode, but exactly one Majorana zero mode, And that does not have a sensible Hilbert space. Okay? Majorana zero modes can only come in pairs. We can basically do this by contradiction. Suppose that you did have just one Majorana zero mode. That means that you should have an operator that, if you start from one ground state, you can then act with that Majorana zero mode operator, get to a ground state that has the opposite fermion parity. That's clearly a physically distinct state. But this zero mode operator does not have a well-defined occupation number. Right? You don't have a way of labeling the Hilbert space associated with those two states unless you have another Majorana zero mode operator that you can assemble into a conventional fermion operator that has a 0 or 1 occupation number. Yeah.
I understand why this makes sense. It's just the notion if I just apply some flux, then I should be able to switch between the conditions.
Yeah. Hold that thought. Yes, exactly. Okay, yeah.
Regulate curve that is set to do the fact that this is fermion?
Okay, thanks for the question. You might ask, how can it not be periodic boundary conditions, right? This is the most natural thing. Typically you would just assign periodic boundary conditions without even thinking. So how do you get that minus sign? And I don't have a very intuitive answer, but I will try to give you some intuition. So if you were actually going to construct this from the point of view of a Bogoliubov-de Gennes Hamiltonian, which if you wanted to do this microscopically, that's what you would want to do. That Bogoliubov-de Gennes Hamiltonian is written in terms of a two-component spinner, which you can think about like an electron spinner. When you go And so that spinner will wind basically by 2 pi when you go all the way around the edge. And when you have a spin a half rotating by 2 pi, you get a minus sign. So that's ultimately how that thing arises. Okay. All right, so this is not okay in this current geometry. But it does not mean that periodic boundary conditions are irrelevant. We can activate periodic boundary conditions in a manner that was just alluded to. All right, so now I'm going to dress up this. Actually, let me draw this bigger. All right, so here's just an enlarged version of my 2D topological superconductor. Now I want to start drilling holes into the center of the system. So let's drill a few of these holes. And by drilling holes, I've now created new boundaries with the vacuum. And so every boundary with the vacuum has to have its own chiral edge state. And so I'll get a new set of chiral Majorana fermions along those holes. Okay, and by the same logic, each of those chiral Majorana fermions has to exhibit anti-periodic boundary conditions. Right? Now, suppose though that I thread a single superconductor flux quantum h over 2e through, let's say, that bottom left hole. Right, so the meaning of that, well, first of all, that's the minimum amount of flux that a superconductor will allow to pass through the system. You can ask, well, why? Why can't I, why won't it allow smaller fluxes, non-trivial fluxes to pass through? And the reason is that if you're a Cooper pair and you move all the way around an h over 2e flux, you feel a trivial Aharonov-Bohm phase. Okay, so you can't actually tell, at least if you're sufficiently far away from that hole, that there's any flux that's been applied. And that's great because it doesn't disturb the condensate and there's no energetic catastrophe that arises. However, if you are not a Cooper pair, but if you're an unpaired fermion, if you move all the way around that hole, you actually get a minus sign. There's a non-trivial Aharonov-Bohm phase that's acquired. Okay? If you're an unpaired fermion, it's h over e, which is invisible to you. But h over 2e, there's going to be a minus sign. Question?
Yeah, how exactly do the Majorana particles couple to the magnetic flux? Because the charge does not.
Yeah, so I'm not claiming that one should actually take derivatives and do minimal coupling. All I'm claiming is that we need to include the Aharonov-Bohm phase of -1 that descends from that flux.
Okay, but can you argue this out a little bit more, or? Is it just some ansatz that you have to?
I would say that this is kind of the. It can't be anything else. This is all I'm using here is Aronoff-Bohm effect, right? And it has. You should be able to recover this from microscopic, more microscopic frameworks. I'm not sure I know how to do that, to be honest, in real time. But I'm sure it's possible to put in flux. But I think a better perspective is to imagine that that there's flux that's it's a little flux tube that never penetrates any part of the actual superconducting part of your system. In which case, it's just a boundary condition effect that you need to enforce on degrees of freedom in your system.
Yeah. Okay. Thank you.
Yeah. All right. So. Question is, where are unpaired fermions? And fortunately, in this problem, we actually have unpaired fermions available at arbitrary low energies in the form of these chiral edge states. Okay. Now, it's handy. You may have seen pictures, I think, from Charlie's slides yesterday. It's handy to think about these minus signs as being accrued when you cross a branch cut that emanates from that h over 2e flux. So let me arbitrarily draw a branch cut that goes from this outer hole to the edge. The meaning of that branch cut is if you take a fermion and then cross that branch cut, you get a minus sign. All right, so in turn, so the boundary conditions, because of that h over 2e flux for this inner hole, are going to be toggled from anti-periodic to periodic, giving me a Majorana zero mode, which I'll call gamma 1, that's bound to that hole. But we avoid the catastrophe that we had previously namely, we won't have an odd number of Majorana zero modes here because there's another edge state that also goes around that h over 2e flux, namely the one that's sitting at the outer boundary. So this edge state will also have its boundary conditions toggled from anti-periodic to periodic, and there will be a second Majorana zero mode that's delocalized around the outer boundary. If you like, you can continue this exercise. You can add an h over 2e flux through this hole. That leads to another branch cut that you can draw emanating to the boundary of your system. Now, in this case, this hole will have its boundary conditions toggled from anti-periodic to periodic. You'll get a Majorana zero mode, which I'm going to call gamma 2. Essentially, this guy will get transported here. And you lose the Majorana zero mode from the outer boundary because now there's, if you trace this chiral fermion, it crosses not one but two of these branch cuts, and so it has its boundary conditions kicked back to anti-periodic. Right?
So basically the resolution is just that because superconductor does not allow me to put in the flux without the hole, I will always have the other Majorana that compensates because I made the hole.
I don't want to exactly use those words because in practice you don't have to drill holes.
No, you can have a vortex.
Yeah.
In principle, it's the same as having a very, very small hole.
Yeah, exactly. Yeah, that's the perspective that I would like to take.
Which is that if I want to have this shift of flux, I will need to somehow introduce another Majorana. I need to kind of correct for this. So
that's right.
The fundamental thing that I cannot shift it is just that's the two mechanisms that go hand in hand.
Yeah. Yeah, that's right. And so what you can see here, maybe you can generalize this. If you have an odd number of h over 2e fluxes in the bulk, that will give you an odd number of Majorana zero modes, and there will be always one remaining at the outer boundary so that you can have an even number of Majorana zero modes and have a sensible Hilbert space. If you have an even number of h over 2e fluxes, then you'll have an even number in the bulk, and you won't have, nor will you need, a compensating Majorana zero mode at the outer boundary. All right, so a small corollary, but important corollary from this is that if you consider superconducting vortices generated by just, let's say, applying a magnetic field to a type 2 superconductor above HC1 but below HC2, then I like to think about those vortices as being kind of self-generated holes. You don't actually need to drill these holes. Any vortex, by virtue of the h over 2e flux that it binds, will carry a Majorana zero mode. Which is, probably the more practical thing that you would like to do an experiment in order to generate these. All right, so any questions about this? And maybe how am I doing time-wise?
Depends how many questions.
Okay. Well, I'm actually at a reasonable stopping point. I can maybe preview what I'll do in the second lecture. So now at this point, we've seen how to get Majorana zero modes in 2 different settings, in one-dimensional topological phase of Kitaev chain, and then in the form of vortices in a 2D topological superconductor. And so the Majorana zero modes that we can generate in that fashion will ultimately give rise to non-abelian statistics of the defects that bind them, either vortices or domain walls in the 1D context. And I'm going to derive, derive in the same sense that I derived a lot of what I'm doing here, kind of use general principles to show how that amazing phenomenon actually arises, despite the fact that this is just a free fermion problem, ultimately. And after that, I will make the leap to topological qubits and show you, what braiding actually gives you in the realm of topological qubits. And with whatever time I have left over, we'll turn to the important problem of what do you do to actually probe these systems experimentally. All right, so that maybe I'll end there and just take questions.
I just have a question, just because I like this idea of thinking of the vortices as kind of self-imposed holes. Just because I've also been working with vortex systems, I'm just kind of wondering if this kind of how to think of this way of it not allowing us to get to this catastrophe happens, and how does it work if I think about not having that outer edge mode, but kind of thinking about having a periodic system in general, so I don't have that outer edge mode. Okay. Because then in principle, what prevents me from drilling one hole? I know that in principle always vortices come in pairs and all this, but in terms of thinking, like you're explaining now, I'm wondering if there's a way to think about what prevents me to drill that hole, or is it just that thinking about that system as periodic without an edge is just completely unrealistic?
My response would have been what you already said, which is that if you try to put this on a sphere,
okay.
You can drill a little hole in the sphere.
Okay. I'm happy.
Okay.
But
any other questions?
Okay, well, thank you.